For this example, we're going to take a look at a couple of vectors in R4. We're going to define the vectors u to be the vector 2, -1, 3, 1, and we'll define the vector v to be the vector -3, 4, 5, 0. Then, using the standard Euclidean product, or the dot product, we're going to find the following. First one is going to be the length of u, or the magnitude of u. For this, because it's the standard Euclidean product, we're going to take each of the entries of the vector, we will square them, we'll add them together, and then take a square root. Same as what we would do for a generalized Pythagorean theorem. So I'm seeing 4 plus 1 plus 9 plus 1, which is 15. So final answer for that length will be the square root of 15. Doing something similar for the length of v. We'll square the entry -3, we'll square the 4, square the 5, square the 0. We're going to add them all together underneath the radical. That'll be 9 plus 16 plus 25 plus 0. Now when we add all of those together, I'm getting the square root of 50. However, square root of 50 can be simplified, and so I'm going to do so. That'll be 5 square roots of 2. Now, for the d of u and v, d of u and v is referring to the distance between u and v. The distance between u and v is defined as the magnitude of the difference between those two vectors. So, going according to the order of operations, I think the first thing I'd like to do is calculate what that difference is going to be. Then we'll calculate the corresponding magnitude. So u minus v is going to be 2, -1, 3, 1. And we'll be subtracting -3, 4, 5, 0. For the first entry, 2 minus -3 will be 5. -1 minus 4 will be -5. 3 minus 5 will be -2. And 1 minus 0 will be 1. Then we'll do the same thing for this as what we did in the previous examples. That'll be the square root of the sum of the squares of the entries. So 5 squared plus -5 squared plus -2 squared plus 1 squared. So I'm seeing 25 plus 25, which is 50, plus 4, which is 54, plus 1, which is 55. So the distance between these two vectors will be the square root of 55. Finally, I'd like to calculate the angle between the two vectors. To calculate the angle between the two vectors, we will need the formula for this, which is that the cosine between, the cosine of the angle between the vectors is going to be the dot product of the two vectors divided by the product of the magnitudes of the vectors. Now we've already got the magnitudes from part A and part B. What we don't have yet is the dot product. So we'll go ahead and calculate that over here. U dot v is going to be equal to, we multiply the corresponding entries together and then add the results. So first components will be 2 times -3. Second components will have -1 times 4. For the third components we'll have 3 times 5. And for the last component we'll have one of my favorite multiplications to do, which is multiplying by 0. Simplifying each of these, we get -6 minus 4 plus 15 plus 0. Combining together, we get a total of 5. Now the one thing I can tell you right away is that because we got 5 here, I know that the angle is going to be acute. This is due to the fact that 5 is positive. If you get a negative dot product, it lets you know the angle will be greater than 90 degrees. It will produce an obtuse angle. So with that in mind, the cosine of theta will then be equal to the dot product, which is 5, divided by the product of the magnitudes, which will be the square root of 15 times 5 square roots of 2 from part A and part B, respectively. Now, this can be simplified a bit. We can cancel out the 5s, leave us with 1 in the numerator. Square root of 15 times the square root of 2 will be the square root of 30. So as far as an exact value is concerned, the angle between these two vectors is going to be the arc cosine of 1 over the square root of 30. However, if you'd like to, you can turn to a calculator and get a decimal approximation for this. Now with that in mind, I'm going to make sure that my calculator is in degree mode. So degree mode, and then I'm going to ask for the arc cosine of 1 divided by the square root of 30. Oops, missed a 3. 30. There we go. And we'll get out of the radical, close the parentheses, and press enter. We do indeed see that we are dealing with an acute angle, and rounding at the second decimal place, it's looking like 79.48. So approximately 79.48 degrees. Now, of course, if you wanted to get radians, well, that's gross. Only mathematicians like radians, which of course is why I like radians, but as far as practical applications out in the real world, degrees are probably going to be your friend.